Thank you, and thanks, thanks, Miles, and thanks also for the very kind invitation to you and to the organizers of the seminar for the kind invitation to speak. Now I'm going to talk about work over the last that I've done over the last year or so with my collaborator Hao Jia. So all of this is work with Hao Jia, who is at University of Minnesota. And I'm going to talk about nonlinear stability of vortices and shear flows, or actually in the other order, shear flows and vortices. Just to, so I'm going to talk what this refers to. So the stability, we are talking about stability of solutions of the incompressible Euler equation in 2 dimensions. And so I wrote it, so it's written here, the incompressible Euler equation is dTu plus, so this is the material derivative of u plus gradient of the pressure is equal to 0. Divergence of u is equal to 0. Now we are going to be in 2 dimensions, and so the most efficient way to write this is dt in terms of vorticity. The vorticity formulation is dt of omega plus u grad omega is equal to 0, and u can be recovered in the usual way as out of the stream function as the gradient perp of the stream function minus dy psi dx psi. So omega is the vorticity and psi is the stream function. Now, of course, we are in 2D, so there's been a lot of work, and smooth solutions are known to exist, and they remain smooth, and that goes back to work of Waldner and Udovich. The vorticity is transported by the flow, and you see this directly from the equation. The equation is dt omega plus u grad omega is equal to 0, so the vorticity is transported by the flow. In particular, it conserves all the LP norms. It basically conserves the size. So if it was like, for example, so it conserves the size, conserves the L2 norm, so the strongest norm, the L infinity norm. What could happen, however, is that the shapes will get more and more rough, and it could lose the derivatives. So the level of the derivatives, of course, one doesn't have control, but one has control of the level of the shape of the size of the vorticity. Now, so the solution exists for all time, so one should think that one can think that this vorticity is transporting and essentially rearranged around as the time moves on. However, what's very hard to determine is the global behavior. So how exactly, so what happens as the time goes to infinity with the solution? It exists, but what happens with it? Does it want to converge? What does it want to do? And there's a general conjecture that I'm going to get to at the very end. It's not really, I mean, it's a conjecture. It cannot, that's, so the intuition which is consistent what we are going to prove in our theorems is that the vorticity would converge weakly as the time goes to infinity. It cannot converge strongly, and it doesn't converge strongly in the models that I'm talking about, but it would converge weakly to some kind of a final shape. So as I say here, the long-time behavior is hard to understand due to the lack of global relaxation mechanism. So the vorticity is transported, but it doesn't relax in any way. Now, what's more realistic is to study the global dynamics close to steady states. So instead of looking at general solutions, we're going to look close to steady states. And there are several important coherent structures. So these are the steady states, such as shear flows and vortices. They are particularly important because it turns out that in simulations, numerical simulations, they have a tendency to form dynamically. And actually, I'm going to show a picture of a numerical simulation. When I get to vortice, I'm going to show a picture of how these vortices form dynamically, and they basically start becoming the dominant feature of the solution. In some ways, it's not true. So at a certain level is not different. It's not very different from the kind of problems that Carlos was talking about, in which at least at a numerical level, one can try to understand what one can hope that this coherent structures emerge as part of the evolution. What we are actually able to prove is if we start with initial data near one of these steady states. Now, this is an extremely classical topic because it turns out that there are many layers at which one can look at. One can look at linear stability, one can look at nonlinear stability, and there are many layers at which one can talk about this. And it's a very appealing problem to study. The first studies of this type go back to the 19th century. There are these studies, these classical studies of Rayleigh and Kelvin, in which these are studies of stability of certain steady solutions, but the stability is done at the linear level. So one linearizes around the steady solution, like for example a shear flow, and one looks at one ignores the nonlinear terms, and one looks at what's called the linear stability. And at the time, in fact, it turns out one was looking actually at mode stability. So one can decompose this further into modes, and one can look at the mode stability. So the two papers that are the classical papers are these two papers of Rayleigh from 1880 on the stability and instability of certain fluid motions, and the paper of Kelvin from 1887, stability of fluid motion, rectilinear motion of viscous fluids between two plates. Actually, one of them, the second one, talks about a problem of Stokes that goes back to 1850s that was related to what the paper was about. And I tried to find, but I couldn't find that other paper. So it goes back too far. Okay, so that's so this is the this was the classical work in the subject. Now to explain, so I'm just going to give just some simple formulas to see what happens. And the simplest way to see it is for shear flows. So shear flows, these are flows U, and so they are flows U defined on. In order to get stability, one has to work on this kind of channel domains in which we have two types of variables. We have a variable that's periodic and a variable that's not periodic. So U is defined on T times some interval I, and it's I could be also the real line, so it could be the bounding interval or the real line. And so there's a velocity field, and a shear flow is a solution. A shear flow is simply a solution of the form B of y comma 0. So B of y comma 0 is a solution of the 2D Euler, and when we try to perturb around it. So we want to understand what happens to perturbation as we start with any stationary solution, and the stationary solution being B of any shear flow, and we perturb around it. Then we can rewrite the equations. So here I'm just rewriting the equation. So omega, so if we move, so this is the level of the vorticity. We move to the level, this was the level of the velocity, we move to the vorticity. So the equation for the vorticity is ct omega plus b of y dx omega minus b double prime of y dx psi. And then plus the nonlinear term, this is the only nonlinear term, mu times squared omega is equal to 0. And omega is recovered as before from psi, from the, I'm sorry, so u is recovered from psi, which is recovered from omega by the elliptic equation. And one has to put boundary conditions. If we are in a finite channel, we have to put boundary conditions on psi. Now, if we look at the equation, it turns out that one case is much simpler than the others, namely b double prime is equal to 0. If b double prime is equal to 0, then this whole term, that's the non-local term, that's harder to understand, disappears. And that's called the Couette flow. So the Couette flow, b of y is any linear flow taking the Couette flow. So b of y is equal to y, or you can put it in the constant times y. But the point is that one gets rid of this term. And if you want to understand just, so my point is just first to understand what happens, so what, this is to understand, to get some formulas, to get the sense for what happens. So let's look at the linearized problem. So we ignore the nonlinear term u times squared times squared omega, and we just look at the linearized problem, which in this case becomes ct omega plus y dx omega is equal to 0. Okay, so this looks very simple. If we are on the simplest case is also when we are on the real line, so when the interval I is the real line. And then the equation is just this simple equation of the real line, which one can solve explicitly. And we have the formula omega of dxy is omega 0 of x minus yt comma y. So that's the formula that solves this linear problem explicitly. Now, to understand, so we move to the Fourier transform. So we take the Fourier. So to understand what I want to talk about now is mode stability. So what does it mean stability for this type of solution? So what we do is we move to, so we look at the kth mode. So we take the Fourier transform, but only in the x variable. So this was the equation. We take the Fourier transform in the x variable. X was a periodic variable, so that's why in order to be able to perform this, we need to work on the channel. So if we look at the k, so the kth mode, we get omega k of ty, and we have an exact formula. Omega k of ty is e to the minus I k ty omega 0 k at y. So now we can study this expression, and they understand. So basically, even from this very simple expression, you understand some of the elements of what's going to happen. Notice when k is equal to 0, there is no evolution. So the 0 mode does not evolve in time. And of course, it cannot go to 0. As I said, there is no relaxation in the problem. It does not evolve in time. It's going to stay as a function of y. It's going to be just a function of y, and it's not going to evolve in time. So the 0 mode stays what we started with. And now something interesting happens to the non-zero mode. So for example, when k is equal to 1, then when k is equal to 1, then the formula is omega 1 of ty is e to the minus I ty times the initial data. Now, when t goes to infinity, so t is very big, this will oscillate very rapidly because there's a coefficient there, it's e to the minus I ty, and it oscillates very rapidly. And as t goes to infinity, this will converge weakly to 0. As I said, the expectation is that one has some kind of convergence. If there is any convergence, this doesn't converge the function e to the I ty doesn't converge to anything, but converges weakly to 0 as t goes to infinity. So that's even in this simple example, we see that if we want to understand the stability, if we want to understand the evolution, we are going to have to deal. Of course, we are going to have to understand the nonlinear level. But even at the linear level, we have to understand. We have to be aware of the fact that the evolution is going to the convergence is going to be in a very oscillatory way and only in a weak sense. Now, there's another way to look at it. So what stability means? Stability means more at the level that the velocity fields go to 0. So let's understand the velocity fields. So I have the formula for omega for every mode at the time. So omega k of ty is e to the minus I k ty omega 0 k. We can write this in terms of the stream function. So we can take the Fourier transform, one more Fourier transform in y, and we can write this in terms of the stream function. So you get that psi is equal to the initial data at the point c plus kt divided by k squared plus c squared. Now, if the initial data was, let's say, smooth, then we can say that this is small except if psi plus kt is of the order of 1. So we can think that psi is about minus kt plus O of 1. And then the denominator gets big. So the point is the denominator gets big as the time goes to infinity. Because this c is minus kt plus O of 1, this c squared becomes k squared plus, so it's k squared times 1 plus t squared. So as t becomes, as t goes to infinity, this denominator becomes very small. So this is how the stream function goes to 0. And now the two components of the velocity field, they can be obtained by taking the derivatives of the stream function. So one of them is going to decay like 1 over t. So think basically k is about 1. One of them is going to decay like 1 over t, and the other one is going to decay like 1 over t squared by looking at this form. So this is the kind of picture we can hope to have. This is the kind of picture that we can hope to have. This is the kind of picture we can hope to develop. That all the modes. So let me write. I think I have it written. So this is what's called the mechanism of implicit damping. All the non-zero modes of the solution of the vorticity oscillate faster and faster as the time goes to infinity, which makes the corresponding modes of the velocity go to 0. Now there is the special mode, the 0 mode, for which this doesn't happen. And for the 0 mode, basically what will need to happen is that that will converge to another function of to another shear flow. So that's. I mean, of course, this is the simplest case. This is the simplest case because we have an explicit formula. The equation is so simple. It's dt omega plus y dx omega is equal to 0. It's a very simple equation. So in this explicit case, this explains how the implicit damping happens. And what we like to understand is basically we want to understand the problem, the nonlinear problem. So this is only at the linearized level in order to have this explicit formula. What we want to understand is to understand the nonlinear problem, and we want to understand. So we want to understand the behavior of the solution in the full nonlinear problem. Now, this is what's called asymptotic stability. So to understand the convergence of the solution of the full nonlinear problem. Now, I'm summarizing here below what are the main issues to understand. Of course, in the explicit model, we don't see them because you can calculate everything. But if we are thinking forward towards the full equations, the full nonlinear problem, and for more general shear flows, then we'll have to address these issues. So I'm going to explain the main issues that we have to understand. Now, the first one, so probably in some sense one of the most dangerous ones is that we don't know what we expect to converge to. If you think that we are starting from a shear flow, there are lots of other shear flows. So any function b of y comma any velocity field of the form b of y comma 0. So any function b of y determines the shear flow. You start near one of them, there is no reason you're definitely not going to converge to the same one. You're going to converge to a new one. So the equation itself, in the nonlinear problem, one has to discover what is the so-called final state, namely what is the shear flow towards which we are going to converge. So that's in some sense it's if you think even when there are there's an infinite family. So as I explained here, there's an infinite family of shear flows to which you can converge. So it's kind of the possible space of final states. Even if you just think of analytic functions b of y, there's an infinite dimensional family of possible final states. So that's one thing that we need to understand. Another thing that we need to understand is the boundary, the effect of the boundary. It turns out it's non-trivial. So all of this calculation works very nicely because the interval I is the full real line, and then all the formulas work nicely from there. It turns out that if that's a good problem. However, the Euler solutions in this case, they don't have finite energy. For the Quet flow doesn't have finite energy if one looks at it on the infinite channel. If you want to work with finite energy solutions, then one has to reduce to finite channels. And it turns out that the boundary of the finite channels disrupts this mechanism. This mechanism is extremely delicate. This mechanism in which the high modes, they go to high and higher frequency in a very controlled way, and that the whole picture doesn't explode, you don't lose control of the whole picture. So there's this very controlled way in which things go to high frequency. And that's disrupted in certain ways by the presence of the boundary, so we have to understand that as well. So now I'm going to get to the main theorem. Oh, before that, just to talk about some of the literature, there are lots of results. There are lots of results on the linear stability, and they go back to the papers that I talked about, the papers of Rayleigh and Kelvin. There are also classical papers of Orr, Taylor, Fadday, McWilliams. There are lots of stability at the linear level. One can do mode stabilities. There are lots of. It's a very appealing problem at the linear level, and even in the last few years of here, the first reference, they go back to the 19th century. This all of these other references, the last references here are in the last 5 years. There's been work of Bedrosian, Cortizellati-Vico, Zillinger, Grenet, Guyen, Rousset-Sofer, and Wei Zhao. And some of these authors, they have more papers, multiple papers. So at the linear level, there are lots of results, and one would say that by now we have there are lots of results that describe the stability of certain flows, going also in 2 dimensions, 3 dimensions, Euler, Navier-Stokes. So there are various problems one can look at. There's a result of Arnold at the level of orbital stability. So it's a general nonlinear result using an energy method, the energy Casimir method. Now, the orbital stability does not describe this picture of convergence towards a final state. It's more like it's going to stay in a neighborhood of these shear flows. So as I said, at the linear level, there are lots of results. I'm actually going to talk about the nonlinear problem, and for the nonlinear problem, there are only 3 results. So it's much easier to capture, to talk about all of them. The only 3 results, all of them in 2 dimensions for the Euler. The only 3 results for the Euler equation, all of them in 2 dimensions. For the Navier-Stokes, there are more results. I'm going to say a few words about this at the end on the last slide. And but for the Euler equation, the only 3 results, all of them in 2 dimensions, is the pioneering work of Bedrosian and Mahmoudi from 2015. So it's a very remarkable paper in which they proved that the Couette flow, the one that I described the linear problem for, they studied the Couette flow in the infinite domain, the torus times the real line, and they proved that in fact one has full nonlinear stability in that case, not just the linear problem. Of course, it's explicit, so that's clear what happens. But they proved nonlinear stability for the they proved nonlinear stability for the Couette flow. Now, as I said, the Couette flow doesn't have finite energy. If we want to work with finite energy solutions, then we can work with the finite channel, and the channel here is finite in the sense that the interval, so it's a channel, so it's periodic in one direction. In the other direction, the interval is from 0 to 1. And our goal, so this is how Haji and I started working on this. Our goal was to understand understand whether one also can have nonlinear stability in the case of finite energy solutions. There's what's called the theorem of point vortices, and that's also work with Haji. I'm going to talk about it at the end. Point vortices, they are not related to shear flow. So it turns out that they are related to vortices. Vortices, what happens for the 2D Euler, any radial function is a stationary solution. So one can think that any radial function in the plane is a stationary solution. So one can perturb around radial functions. It turns out that's a very tough problem, but what we can do is perturb around delta functions, and those are the point vortices. And then the theorem I'm going to start with, which is the general monotonic shear flows, which satisfy a spectral assumption that gives linear stability. And so this also works with Haji, in which we prove global stability for a general class of monotonic shear flows satisfying a linear assumption in the finite channel T times 0, 1. So this was work from January and independent work of Mahmoudi and Zhao, who proved essentially the same theorem. So so the work was independent, but the theorem turns out to be almost identical, except for maybe the topologies in which we measure the perturbations. Otherwise, all the important assumptions, they are identical. So this was work from January this year. And that's the one I'm going to start with, the theorem on general monotonic shear flows. So I'm going to start by stating the theorem, and then I'm going to explain it. But so let me state the theorem. So you're looking at vorticity omega naught. Omega naught is the initial data. We're looking at 2D Euler, so we're looking at vorticity, which is defined on the channel, so T times the interval 0, 1, but is supported strictly inside. So this boundary effect that I want to, so we have to account for, and so the vorticity itself supported strictly inside, so it's supported in this interval T times 2 var theta and 1 minus 2 var theta, and it's small. So there's a smallness condition on the vorticity, and it's small in a norm that I wrote here, the Gevrey norm of the Gevrey 1/2 norm. I'm going to define it on the next page. It turns out that one thing about the nonlinear stability, which happens for all of these problems, is that one has to work with Gevrey classes. One is infinite differentiability. There's a certain interaction that cannot be. There's a certain so-called reaction term that requires that in order to be able to control it. So we are looking at the solutions with in a Gevrey class, and then the conclusion is that there is a global solution. So there is a global solution of the Euler equation. Here I just rewrote the equation, dt omega plus b of y dx omega minus b double prime of y dx psi plus u grad omega. So this is the Euler equation, and psi is recovered from omega from the Laplace equation. Delta psi is equal to omega, and on the boundary we have this boundary condition: psi at 0 and psi at 1 are equal to 0. Now the function b is going to be monotonic. So one thing that's the whole mechanism of implicit damping only works for monotonic shear flows. So the function b is going to be monotonic, and it's going to satisfy another condition that I wrote. It's on one of the next slides. It satisfies a linear stability condition. So we need to assume somehow then one doesn't have non-decaying modes. So it's a spectral condition on B that guarantees linear stability. Okay, so then the conclusion is that there is this global solution, and moreover, the support of omega still stays for all times bigger than 0. The support of omega still stays strictly inside, just expands a little bit, but still stays strictly inside the channel. Moreover, it converges after suitable renormalization. It converges to a final. This F infinity is the final state. It's the final state of the vorticity. It converges after suitable renormalization. And as I said, finding the final state is not an easy matter. In this case, we have to unwind the linear flow, so it's x plus tb of y, but there's also a nonlinear correction that depends. So morally, to find the final state, the solution has to go through the whole evolution, and then this function capital phi gets constructed, and that's what eventually leads to the final state. And we have a certain speed of convergence, so then we get that omega after this renormalization converges to a final state. So this is the asymptotic stability part at a certain speed. Moreover, once we have the information about omega, we can go back and derive the information about all the other pieces. So we have that we can construct the function psi infinity. So that's the final state of the stream function by solving what would be the equation, and then we can say that the zero mode component of the zero mode component of the ux velocity field converges to this final state, and all the other parts converge to 0 at speeds of 1 over t or 1 over t squared, depending on which components we are looking at. So that's this is the asymptotic stability part. The hardest part is to show that the vorticity converges after these renormalizations, and after that the other parts describe the rest of the components of the system. Okay, so that's the theorem that we prove. Nowadays, so I have to explain two things, namely what is Shear regularity, so what are these norms that we work with, and then what are the assumptions on the shear flow that we have to make. So the Shear regularity, it's defined here, so it depends on the main exponent is S. So we take a function. It can also be defined in the physical space, but it turns we work with it in the Fourier space. So in the Fourier space is defined in the following way: we take a function, we take its Fourier transform f tilde. F tilde depends on k and psi. So k is from the periodic variable and psi is from the real variable, and then that gets multiplied by an exponential. So instead of multiplying by a polynomial of k and psi, as we will do for the Sobolev space, you have to multiply by this exponential. The main exponent here is S, and there's also the exponent lambda. So there are two exponents in the Shear norms. And if one is to describe this in the physical space, then this amounts to assuming all the derivatives, not just finitely many. So all the derivatives, one assumes control of all the derivatives depending on how high you go in derivatives. There's a way to describe this in the physical space as well. And as I said, Shear regularity is needed in all the nonlinear asymptotic stability results. And there's some recent work of Deng and Masmoudi that confirms that. It turns out that if one wouldn't assume Javer regularity, one would be able to control a certain cascade in the nonlinear problem. Okay, so this is the smoothness that we work at. Now the function B that I talked about. So what is exactly the shear flow we are talking about? Now this function B has to satisfy conditions which are actually necessary. First of all, it has to be smooth enough, slightly smoother than the solution. So it's going to be smoother. Better not is going to be a big exponent, so it's going to be slightly smoother than the solution. It has to be monotonic, so B prime is between two constants bounded away from 0. And it has to be linear around the boundaries in order for the whole situation to be stable. If it was not linear around the boundaries, it would contribute, even though we start with the vorticity being supported strictly inside the channel, it will immediately hit the boundary, so that the assumption will not matter. So in order to keep the situation stable, it has to be linear around the boundary, and it has to be strictly monotonic. And now the spectral condition is that if we look at the following linearized operator, and I wrote it here for every mode at a time. One can write it in general without decomposing modes as well, but I wrote it on every mode at a time. The following linear operator, B of y times f minus B double prime of y times phi k, where phi k is obtained by solving what would be the corresponding Laplace equation for the kth mode. So dy2 phi k minus k squared phi k is equal to f. So this linearized operator has no discrete eigenvalues. If there were discrete eigenvalues, you wouldn't have the problem. No, you wouldn't have even at the level of linear stability. You would not have linear stability. So both of these conditions are necessary in order to have nonlinear stability. And the theorem that we have is that, so more the theorem that we have is this: we have enough information to prove linear stability, then we can prove nonlinear stability. So that's, if you want, morally the theorem. If we have enough information about the shear flow to be able to conclude linear stability, and if the data was smooth enough relative to this Javer norms, then we prove nonlinear stability. Okay, so that's I'm going to spend a couple of slides now talking about some of the main ideas of the proof. So this is the main theorem. I'm not going to spend a lot of time because actually I wanted to get to vortices as well. So just so now we have to. So we look at the look at this equation. So the equation is this equation dt omega. And in order to be able to study it, we need to eliminate the non-decaying components. There's a non-decaying component here, b of x, b of y dx omega, and there's one more nonlinear. Nonlinear decaying component coming from the fact that q does not, coming from the last term. And to do that, so we need to eliminate them. So we make a change of variable, and the change of variable in order to basically get to the convergence is. So v is b of y plus this nonlinear part that's going to be recorded eventually in the final state. So this is the new variable, the new periodic variable. I'm sorry, the new non-periodic variable, and z is x minus tv that unwinds the flow, and that's the periodic variable. And then we construct the new variables. So we make a change of variable, and then we construct the new variables. The new variables are f in the new variables corresponding to omega, and phi corresponding to psi. And then we have to keep track also of all the change of coordinates. So v, these are non-linear change of coordinates here that we have to track as well. So we have functions v prime and v double prime and v dot, which keep track of this. And so the profile, what we construct this way, it's called the profile, because what we want is to show that phi converges, the f converges. So after we make these changes of variables, we want to show that f converges, and the profile is going to satisfy this equation dtf. All the other linear part was removed, and then but we still have the one linear part coming from the non-local component dtf minus b double prime dz phi is equal to these non-linear terms, and the phi itself can be. So the stream function itself can be recovered from f by solving this elliptic equation. And one also is, it turns out one also is to write equations for the coordinate functions, so the variables v prime and v dot also satisfy suitable equations. Now, there's a main difficulty, namely this is not exactly, so the profile, we don't have, there's this extra term that comes in the linear part. And in order to study it, which only happens because the flow is not only, if we were in the quet case, then this term would disappear. So that's in some sense the main simplicity of the quet flow, that one doesn't have to deal with this non-local term. But in our case, we have to deal with it. And the way we do this, we construct auxiliary profiles, and so we construct an auxiliary profile. F star is F minus, and we subtract all this contribution. So it's F minus B0 double prime. In fact, we also freeze the coefficients. There's an issue with freezing the coefficients that's a little more technical to explain. And then we also construct an auxiliary stream function phi that solves almost the same equation, but with certain coefficients being frozen at time t is equal to 0. So that's so this is our construction, and now we want to control all of these quantities, and the way we control them using so you prove bootstrap estimates using energy norms. So everything is based on using energy norms, and all the energy norms are done in the Fourier space, because it turns out that there is what's called the resonances, which can only be detected in the Fourier space. All of the energy functions that we look at, they are done in the Fourier space, and they are of this type. So we have, for example, I wrote here the one for for the one for capital F, it would be, so look at the Fourier transform of F at tk(c), so you take the Fourier transform in both variables, and you multiply with a certain weight ak. And so this gives an energy at time t, and you also have to track the contribution of all the bulks. And the contribution of all the bulks, these ways depend on the time, and they are decreasing in time. So it turns out when we take, so the contribution of the bulks is measured by taking the time derivative. So this ak dot means the time derivative of the weight ak. Now, the choice of these weights is extremely important, and it's dictated by the resonances that we have in the nonlinearity. And to see them, if we think that even in an ideal situation, if the equation for phi was, if we pretend that v prime was equal to 1 and v double prime is equal to 0, then we could solve this equation explicitly in phi, and we would get that phi tilde is f divided by k squared plus c minus kt squared. And what are the resonant times is when phi is too big. So if c minus kt is small, this means that t is of the order of t is close within unit of c over k. And in that case, the function phi is not small. In fact, it's not small. You need the function phi to be small because it needs to be integrated, and one has to avoid the loss of the derivatives. And in that range, the function phi is not small. And this is a reaction term. That's one of the terms in the equation which contributes the worst, because it has a derivative of phi, and there's no symmetrization possible at this stage. And the only way, so this is actually the key idea of Bedros and Masmoudi, the only way to do this is to work with what's called very unbalanced weights. So the weights have to be very far from being constant. They have to satisfy inequality of this side, that the weight, the AL weight is controlled by the AK weights. And so the weights have to satisfy inequalities that are in some sense very unbalanced. If you think the enemy here is when eta over L is close to T, then there is no denominator here. If L is about 1, then what we are saying is that the weight at eta is eta times the weight at C. So if C minus eta is of size 1, then that gets to be quite tricky. So the construction of the weights is trickier. And we actually, so in our problem, it's quite a bit tricky in the quet flow, because one has to, it's a variable coefficient problem. So one has, and we still need to work with the Fourier transform. So that leads to, so the construction of the weights is tricky. I don't want to get into the into the technical details, but that's where the Gevrey regularity is needed, because you need this way to satisfy lots of properties of this type, and the only way to fit them and not destroy everything as the time goes to infinity. The only way to fit them is if you start with the exponential regularity, so Gevrey regularity. It's at this stage that one is Gevrey regularity. Now going back to this, so basically, what we do is we look at this auxiliary profile that I said that we defined. So I just rewrote the equations that we had on the other slide. So dtf minus b double prime dz phi is a nonlinearity, and we define this auxiliary profile. The auxiliary profile is not going to include this term dz phi, which is the unwanted linear term. So we can basically control this auxiliary profile as part of the bootstrap argument. Now the key issue is to control the difference between the real profile and the auxiliary profile, and here we need to use the spectral assumption. So use the spectral assumption. So we use the DML formula, and we rewrite the equation. So you rewrite the equation for. It turns out that we want to use the DML formula. And we use the DML formula. We are led to this kind of linear equation for every mode. We can decompose in modes, so we can write the equation for every mode at a time. And the main idea is that, of course, you cannot solve this explicitly. This was the difficulty to begin with, but we can still have a representation formula in which we represent the function gk in terms of a certain kernel pi. The important one here. So this is the initial data, but the important one here is the kernel pi. And the kernel pi is not explicit, but we can write it in terms of the spectral representation formula, and eventually we can prove bounds on it. So even though it's not explicit, we have a formula that, so we have a certain formula in the Fourier space that allows us to prove bounds. And once we have this, so we can put together so we can look at the difference between the real profile and the auxiliary profile, and eventually we can control all these functions, all these functions using the bootstrap argument. Okay, so these are the main ideas in the proof of the theorem. Now, what I wanted to do was to talk a little bit about vortices, because vortices, in my mind, they are the nicest problem about 2D Euler. So the last couple of slides, I'm going to talk about vortices. Now, vortices, you can think of vortices are just any radial function at the level of the vorticity omega would be a solution of 2D Euler. And so vortices, now the question is which ones are stable. Of course, not all of them are going to be stable. They need to have some properties. Like, for example, they need to be radially decreasing in time. Now, 2D Euler is simple enough that we can do. There are numerical simulations that show what happens with general flows, and I'm going to do this. And now I want to share the other screen. Just a second, share the other. So this was starting out as a general solution of the. We started with general initial data this was in a periodic setting, and in fact it was not Euler, it was Navier-Stokes, the very small coefficient. And this is what happens with the general solution. These are vortices, the guys that form, they are vortices, so they are radial functions, and they move around, and they keep interacting. There are two colors, so the one of them is positive, the other one is negative, because of course the vorticity is transported, so the positive part is and the negative part, whatever is positive stays positive, what's negative stays negative. So that's what you saw is that what happens is that what we saw in this simulation is that at the end of the day there are only two vortices left, and that's so the evolution is going to be, and they never collide anymore because one of them is positive and one of them is negative. So that's so this is why vortices are important, as I was saying at the beginning. Vortices are important for the nonlinear evolution because in some scenarios one can see how they form. It's almost like the soliton resolution that it's of the same type as the soliton resolution that Carlos was talking about. Now, of course, we cannot prove anything close to this, and we are very far from being able to prove anything close to this. But what we can try to prove is to prove at least that vortices are stable. And even that is it's a very hard problem. It has been looked at the linearized level. So so there's this paper, this very recent paper that a couple of years old of Bedrosian, Cotizzelati, and Vicor, who proved that at the linearized level, so if one looks at the linearized stability around the vortex, and if the vortex is decreasing, radially decreasing, what makes them stable is that they are radially decreasing. This is the analog of the monotonicity of the shear flux. So if they are radially decreasing, then Bedrosian, Cotizzelati, and Vicor, they're able to prove that one has linear stability. Even that was not at all an easy theorem, so it's more than 100-page long. So even that was a pretty complicated theorem. But at the linear level, they're able to prove linear stability. Now, we are not able to prove nonlinear stability yet, but we are able to prove nonlinear stability in the case of what's called point vortices. So instead of thinking of a general vortex, we think of a delta function. We think of the delta function is radial. If it's radial, it doesn't interact with itself. So the equation that, so the vortice, the object, the vortice you are thinking about is a non-zero multiple of the delta function plus a smooth vorticity. And then we prove global stability of this structure, that if we start with the delta function plus a smooth vorticity, then so if we start with the delta function plus a smooth vorticity, then the delta function is going to move. So the vortex itself is going to move, and the vorticity is going to become, is going to converge to a radial function around the new vortex. So here I have the main theorem. This also work with Hauer-Shear, that the equation dt omega plus u grad omega plus this is the nonlinear part. So this is the equation for omega for the vorticity, and then we have an equation for the center p of t, and p prime of t satisfies this other equation. P prime of t is the gradient perpendicular of psi. And the theorem that we have is that if we start the smooth compactly supported perturbation away from the center from the vortex, then we can which is small and smooth in this Gervais space. Then the whole picture stays stable. So the vortex itself is going to move towards a final state, and the vorticity is going to move towards a radial function relative to the new vortex. And there's a new component in this proof that I'm not going to have time to explain. There's a new component, namely that the vortex itself moves. So we need to understand the motion of the vortex. It turns out that the convergence has to be extremely fast in order not to disturb the other things. And so that's so my hope is that this will be a step towards understanding the full stability of vortices problem. Now, so that's this is my last slide with some conclusions and some other problems that are related to what I was saying. So at the nonlinear level, inviscid is a very delicate global stability mechanism. It's very delicate because the vorticity, the only way to make it work, the vorticity is required to go to higher and higher frequencies in a precisely controlled way. So something is exactly the opposite of what you want to do in a dispersive equation, where we want to say that the vortice that the objects don't go to high frequencies. Here, one has to get them to high frequencies, and they leave very little behind. So far, this has only been implemented in the case of 2D evolutions. For 3D evolutions, 3D Euler, 3D evolutions, this has not been done at all. What has been done in the case of 3D is to look at the corresponding Navier-Stokes instead of the Euler, and then say that the perturbation is small relative to the viscosity coefficient. And then if it's small enough, like relative to the suitable power of the viscosity coefficient, then one can still prove stability. Now, all the theorems that we proved are consistent with the general conjecture that I mentioned in the beginning, that generic initial data, the solution converges weakly but not strongly as time goes to infinity. Of course, there's no way to prove something with the generic initial data on has this kind of convergence. The only way to prove would be to disprove it, I think, to somehow show that it doesn't happen. But in any case, what we've done, so in all of the situations, we were able to describe the dynamics for a long time. This actually holds true. Now, this, as I said, there are only very few theorems at the nonlinear level. We don't know anything in 3D. There's this, what I find is like a very interesting, very beautiful problem in 2 dimensions, namely to prove nonlinear stability of smooth and radially decreasing vortices. So these are the ones that are expected to be stable, the ones that are smooth and radially decreasing. Also in 2D, there's the problem of non-monotonic shear flow. So everything that I've done, that I talked about so far, relies on this implicit damping, which is something that has to do with monotonicity. But there are also very important flows that are non-monotonic, like for example, the flow corresponding to B of y is y squared, which is called the Poisson flow. That's non-monotonic, and it's not known if one can have nonlinear stability in this case. Okay, so that's so this is basically okay. It's my last slide, and I'm going to stop here. Thank you.